In this video, we're going to talk about compound interest problems, which we already did talk about quite a bit, but the way that this book is set up, we're doing it again. For some reason, the book decides to write the formula differently in section 3.2 than it does in chapter 2. So I'm putting this on here just to kind of point it out to you that if you use any of the help functions in the homework problems, that this is probably the way that you're going to see it. I don't necessarily recommend thinking about it this way. It's the same formula, it's just written differently. So what they're doing is they're using I here to equal R over M. So remember, R is interest rate and M is how many times interest is compounded per year. So they're just replacing the R over M with this I. And then the other difference is that the N here is the total number of compounding periods. So they're using N instead of M times T, which also is kind of confusing because a lot of times we use N instead of M, but that's what they're doing here, is they're just making less variables by making some variables represent two different variables. It's a little weird, but don't let it freak you out. It's the same compound interest formula that we used before. And then we also have the same continuous compound interest formula if interest is compounded continuously, which is A equals P times e to the RT power. So our first problem here, we're looking at an individual retirement account which has $200,000. The owner decides not to add any more money to the account other than interest earned, 6% compounded daily. How much will be in the account 35 years from now when the owner reaches retirement age? So this is actually a fairly common scenario when you have an retirement account at a company and then you switch jobs. You might roll your retirement account over to an IRA, but you're not putting more money into that IRA. You're just earning interest on it. So I'm plugging in $20,000 for my principal, my starting amount. Then I'm going to have 1 plus interest rate of 6%, 0.06. My compounding is daily, so that means my M is 365. I would not try to divide this and get a decimal value for I. The rounding there is probably just going to be kind of ugly. So I recommend just plugging in the R over M like we did before. 365 and 35 years, so 365 times 35 is going to be that N or that M times T. So that's going to be my formula. Plug that in on a calculator. I put parentheses here around the exponent. Make sure that you do that as well to get the right answer. And I would find an answer of $163,295.21. So if I start with $20,000 when I'm changing jobs or whatever, 35 years later I will have $163,000, and that is just interest earned. So it is 8 times what I started with, essentially, just from the interest that has earned on the account. I'm not putting any more money in. That is all interest. So as you may have heard, saving for retirement, it's important that you start early because that time is the key. When it's in the account for so long, you can really build up a lot in interest. Question 2. Over a 10-year period, a $10,000 investment in a growth-oriented mutual fund grew to $126,000. What rate compounded continuously did you earn? You will need to use natural log to solve this problem. So now I have my amount in the account, $126,000. I have $10,000 is my principal, my starting amount, and interest is compounded continuously. That means we're going to use the P times e to the RT formula. So E, remember E is a number, not a variable, so we're not plugging in for E. And then the power is R, is what I am solving for, the rate. the time is 10 years. So R times 10. And we're solving this equation for R. So I want to get R by itself. I can do that by first dividing both sides by 10,000. So I want to get rid of that 10,000. And that gives me 12.6 equals E to the 10R. I'll just write that R times 10 is 10R. So now here is where the logs come in. So remember, when we're looking at logs, we can write log. I'm going to write log base E first just so you can see where the base is. So E to the 10R power equals 12.6. So when I write it as a log, it's log base E 12.6 equals 10R. Remember, the answer to the logarithm is the exponent. So think about where these three numbers are going. This one is a little bit uglier than the ones that we did before, but we still have three things here. 12.6, we have the E is the base, and we have the answer to the log is the exponent, which is 10R. And then, since this is log base E, I know that's natural log, so I'm going to replace log base E with ln, and I'm going to use the ln button on the calculator. So ln of 12.6 equals 10R. Last step to get R by itself is to divide both sides by 10, and I have R equals ln of 12.6 divided by 10. So on my calculator, remember, the ln button is under the FUNC. I have ln of 12.6, close that parenthesis, and then divided by 10. So we have 25.34 or 337%. So pretty high interest rate, especially over a 10-year period. That's a pretty well-managed fund, I suppose. 25.337. Make sure that you are paying attention to where problems want you to round numbers. If it's to 3 decimal places, then that's what this one would be.